Hi again. This video is from Chapter 6. It is problem 6.25, A and D, very similar to 6.25 on Mastering Chemistry. Comes from section 6.4 in your textbook on Charles's Law. Charles's Law states that temperature and volume are directly proportional. So if temperature increases, then volume will increase, and vice versa. Okay, if the pressure and the amount of gas are held constant. Okay, and so if we look here, this problem says that a sample of neon initially has a volume of 2.50 liters at 15 degrees C. What is the new temperature in degrees Celsius when the volume of the sample is changed at constant pressure and amount of gas? Okay, the key here is that it wants the answer in Celsius, but you can't just plug in Celsius into the equation. All of your gas laws, you have to plug in Kelvin into the formula first, and then you can convert to Celsius. Okay, so if we look at the equation for Charles's Law, okay, so in your book it has it written as V1 over T1 equals V2 over T2. And if we rearrange this, I like looking at this linear. So if we say, this is how I like to look at all of the gas law formulas. Okay, and so it looks like we're trying to find T2. So if we rearrange to solve for T2, okay, one of the most common mistakes is just to accidentally put in, V1 instead of for V2, or you get your volumes and your temperatures mixed up. So I like to go through and we'll say here that our V1, this is our initial volume, and our T1, okay, and then our V2 is 5 liters. This is what problem A is asking us, if the volume is 5 liters, or it changes to 5 liters. Okay, and the next thing we have to do is we have to convert Celsius to Kelvin. So we take 15 degrees C plus 273 equals 288 Kelvin. Okay, so now we're ready to plug this in. So we find that our V2 is 5 liters, our T1 is 288, and our volume 1, 2.50, and we get 576 K. Okay, the question's asking us for Celsius. Okay, and so now we convert from Kelvin to Celsius by subtracting 273, which would give us 303 degrees C. And when you're converting from Celsius to Kelvin, we add 273. And if you're doing the reverse, if you're converting from Kelvin to Celsius, then you subtract 273. Okay, but the key is that you have to plug in Kelvin into the equation. You cannot plug in Celsius. And for D, excuse me, this should say D there. Okay, we are going to do very similar. So it's still the T2 is what we're solving for. So if you look back at the previous slide, we rearranged our equation to look like so. And 2.50 is our V1. And we converted already to 288 Kelvin. This is our T1. Okay, and 3,550 milliliters. This is our V2. Okay. However, we have to have our units of volume the same. Okay, in this formula, it doesn't matter if it's milliliters or liters, but it's probably good to go ahead and use liters. Okay, so we'll go ahead and just convert to liters. It really doesn't matter, but that just, other at gas laws, you have to convert to liters, so we'll just go ahead and convert to liters. So we've got to move our decimal place back 3. So we divide by 1,000. So this gives us 3.550 liters. Okay, and this is our V2. So we get 3.550 liters times 288, so our T1, 288K, divided by V1, which is 2.50 liters. So we get about 408.96, or you can go ahead and round that to 409 if you would like. We subtract 273, and we get 136 degrees C. This is what we get in Kelvin. We subtract 273, and we should get 136 degrees C. And that wraps up problem 6.25.